Okay, so we have seen how a function that is analytic at some point has derivatives to all orders at that point, right? So there is an immediate consequence of this is that a Taylor series of such a function about such a point of analyticity is always available, right? So that's what we will discuss in this lecture. So if a function is analytic inside some disk, right, mod of z minus z naught less than r naught, which is centered at about this point z naught and with radius r naught, right? So then f of z is guaranteed to have a convergent power series representation. F of z is equal to summation over n going from 0 to infinity n z minus z naught the whole power n, which is going to be guaranteed to converge inside this disk, right? So the function is analytic everywhere inside the disk. Okay, so this function has this power series representation and which is guaranteed to converge within this region mod of z minus z naught less than r naught, and where an is given by all these derivatives. So we've already seen that all of these derivatives to all orders exist, therefore it's completely well defined. So you have an explicit representation for all these coefficients and there is no difficulty with convergence as long as mod of z minus z naught lies within this region of analyticity, right? So I mean, we will not go into the details of proving this result, right? But we will take this as a given, right? So in fact, this is a characteristic of analyticity is, Cauchy theorem holds, also the existence of derivatives to all orders. Inside the region of analyticity, there is a path independence for these contour integrals, existence of Taylor series, expansions which are convergent. All of these are automatic features of analytic functions, right? So even if you are working with a function of a single variable or just a function of two variables, let's say, to compare with f of z, right? So then for a Taylor series expansion to be convergent, right? So you have to work with there are conditions which go into this. I mean, you can have functions which are once differentiable, twice differentiable, or thrice differentiable, but then suddenly their differentiability is lost and so on, right? These kinds of complications are there for functions of a single real variable, for instance. But on the other hand, if you have a function of a complex variable which is analytic, then you are guaranteed that its derivatives to all orders exist and also Taylor series which is convergent is available. So of course, yeah, so this is really a generalization of the notion of a Taylor series of a function of a real variable, but we see that it's guaranteed to converge, right? And all these inside a region of analyticity, and it's closely related to the fact that you have all these higher order derivatives available. So we can write this out explicitly and write it as f of z naught plus f prime of z naught divided by 1 factorial times z minus z naught plus so on, right? And mod of z minus z naught is less than r naught. So this r naught is something that has to be decided from a on a case by case basis. So you have a region of analyticity, so you're guaranteed that this r naught has to be greater than 0 because you're at an analytic point. We know that analyticity immediately implies analyticity inside a neighborhood around a point, the point of interest. That region of analyticity, the radius could be small or big, but it has to be greater than 0, right? So that's within the very idea of what analyticity is. And so there are cases where this r naught can go all the way up to infinity, right? So in particular, if you have an entire function, then you have Taylor expansions available for this function about any point in the plane, and all of this different kinds of series that you can write would converge in the entire plane, right? So if we expand a function about the origin, then the Taylor series is called a Maclaurin series, and it looks like this: f of z is equal to f of 0 plus f prime of 0 over 1 factorial z plus f double prime divided by 2 factorial z squared and so on, right? Mod z again, less than r naught, where r naught is this radius of convergence as it is called. Okay, so let's quickly look at a few examples. So we have seen that the function f of z is equal to e to the z is entire, so it has a valid Taylor expansion about any point in the complex plane, any finite z, and the derivatives of this function to all orders are also immediately written down. They're simply e to the z. Therefore, expanding about the origin, we have the Maclaurin series as e to the n divided by n factorial. Right, so you could also, work out the expansion about some other point. So in place of z to the n, you will have z minus z naught the whole power n, and it's just a matter of sort of shifting z to z minus z naught, right? And then you will see that this is according to this Taylor expansion. So let's look at another example. So if you want to expand a trigonometric function, so we have seen that trigonometric functions are entire, because after all, trigonometric functions sine of z are defined in terms of exponentials, both e to the iz and e to the minus iz. They're entire. It doesn't matter whether you take the argument to be iz or z. It's a complex number. Exponential of a complex number is well defined for all finite values of z, and therefore it's an entire function. So the linear combination of of entire functions is also entire. So sine of z is entire, cosine of z is entire. So sine of z, the expansion, the Taylor series expansion of sine of z can be immediately written in terms of the Taylor series expansions of these exponentials, right? So while in general one has to take special care when if you're trying to add two series, can you add them term by term and all this, but so for our purposes, let's take this to be a given, and it is indeed true for this case. And so you can actually combine these two term by term, and then you get I to the iz the whole power n minus iz the whole power n, and then you get a minus 1 to the n, and then only the odd terms will survive. So we can as well write this as z to the 2n plus 1, and a minus 1 to the whole power n comes out. So it's a matter of I to the n minus I to the n. So that will become minus 1 to the n, right? So it will oscillate between plus sign and minus sign. So it's just a matter of seeing that whenever you have an even power, right? So this will vanish. iz the whole squared, for example, is just minus z squared, and minus iz the whole squared is also minus z squared, so it will cancel, right? So but I mean, if you take it to an odd power, then you will get a I which will cancel with this I in the denominator, and then you have a minus 1 to the n, right? So it's something that you can quickly verify, and notice that sine of z is actually just like the expansion we have when you have a the sign of a real variable, which is very nice. And so it's just that this z has been now elevated to a complex number, and it's guaranteed to converge for any value of z, right? It's very nice, and it's it's convenient that our extension of the idea of a sinusoid works out so nicely also for the Taylor expansion. And likewise, cosine of z, you can check directly from first principles, from definition of what cosine of z is, as the sum of these exponentials, again sum of these two different series, and then you get cosine of z is equal to summation over n minus 1 to the n z to the 2n divided by 2n factorial. Once again, it's an entire function, so mod z less than infinity, it's going to be convergent. You can also shift this point about which the expansion is considered to any other finite z naught in the complex plane. So once again, hyperbolic functions, sine hyperbolic of z, cosine hyperbolic of z are also readily expanded in terms of Taylor expansions. Both of these being linear combinations of exponentials are also entire functions, and they have these Taylor expansions, which are completely natural generalizations of their corresponding Taylor expansions for corresponding functions of a real variable. Okay, so let's look at another example. Now this time we look at an example of a function which is analytic, but it's not entire. It's analytic in a region, right? So we see that 1 over 1 minus z is, it has a it's analytic everywhere except at the point z equal to 1. So if you're looking at its derivatives, it's straightforward to write down these derivatives explicitly. The nth order derivative is going to be just n factorial divided by 1 minus z the whole power n plus 1. And again, this is well defined at all points other than z equal to 1. And so we can write down this Maclaurin series f of z is equal to 1 over 1 minus z is just 1 plus z squared all the way up to infinity, right? So summation over n going from 0 to infinity, z to the n, is this function, right? And this function is not entire, and it has a singularity sitting at z equal to 1. So for all mod z less than 1, this particular series expansion will converge, and it will converge exactly to this function, right? So that's the statement of the Taylor-Maclaurin theorem, if you wish. And it's also possible to expand the same function about some other point inside this region of analyticity. For example, you could take this z0 to be a half, and we now have it's convenient actually to rewrite it in this form and use the same result that we already had. Also, you can directly work it out from first principles, work out all these derivatives evaluated at the point z0 equal to half, and then you can actually cross check that you get back the same result. So that's another way of doing it. F of z is 1 over 1 minus z, which can be written as 1 over half plus half minus z, and then you pull out this factor of 2 from the denominator, by a factor of half from the denominator, which becomes a factor of 2 in the numerator, and so then you have 2 divided by 1 plus 1 minus 2z. Now you can actually think of this 1 minus 2z as your as a complex number, right? So it's, instead of thinking of it as f of z, it can be f of w, which is 2 divided by 1 plus w, right? And then you can expand this function in terms of 1 over 1 plus w, right? So in place of minus z, you have a plus w. So you get 1 plus 1 minus 2z. So you have to be a bit careful. So so 1 minus, so it's actually 2z minus 1 plus 2z minus 1 the whole squared, and so on. So let's check this. So we have 1 minus z is good. So it is 1 plus 1 minus 2z. So if you expand it, now this is more like 1 minus 2z minus 1. So this should be it's better, it's more convenient to rewrite this as 2z minus 1, and then you have with an overall minus sign, so it's a minus 1 minus 2z minus 1, and then so that we can immediately connect to this z here, and so now we have 2z minus 1 should be 2z minus 1, 2z minus 1 everywhere, 2z minus 1 the whole squared, so on. The whole power and so on, right? And clearly this series is convergent whenever mod of 2z minus 1 is less than 1, right? So in fact, you can try to expand the same function about some other point. So what we have managed to show is we have this point, so if I take there is a singularity sitting at the point z equal to 1. So if I expand about z equal to 0, then I have found that this series is convergent in this entire circle of radius 1, mod z less than 1, so in the interior of the circle. But on the other hand, for the same function, if I were to expand about this point half, so then I find that it's convergent in a smaller circle of radius, it's supposed to come here, of radius half. And so the same function has a different Taylor series if you are expanding about a different point, and it has a radius of convergence which is half. And so that's what we have found here. 2z minus 1 mod of this must be less than 1. Right, so in this lecture, we have looked at how the idea of a Taylor series can be generalized to functions of a complex variable. We have looked at a few examples of analytic functions, some of which were entire, and some other examples where the function was analytic inside a region, and how a Taylor series is always available for an analytic function about a point of analyticity, and whose convergence is guaranteed inside the inside the neighborhood of an analytic point, as long as there is no singularity there. So inside this whole region of analyticity, around a point of analyticity, this Taylor series is guaranteed to converge. Okay, thank you.